My name is Anis Idrisovic, and I'm currently a second-year PhD student at the Institute of Optics here at the University of Rochester. Thank you for joining us for Voices of XR, a Marianne Mavronek Studio X speaker series. This series is made possible by Kathy McMorran-Murray and the National Science Foundation as a part of our interdisciplinary graduate training in science, technology, and applications of augmented and virtual reality here at the U of R. It is my pleasure to introduce today's speaker, Dr. Sanjeel Parekh. Dr. Parekh is a research scientist at Meta Reality Labs. His work primarily focuses on building machine learning tools for problems involving audiovisual data, such as source separation, event detection, and speech enhancement. He earned his PhD in computer science at the Technicolor and Telecom University of Paris-Saclay in 2019. His thesis was on learning representations for robust audiovisual scene analysis. Other areas he finds interesting and engaging are multimedia, NML research, music, philosophy, math, and machines. His talk today will focus on audiovisual scene understanding and how the field appears through a lens of augmented and virtual reality. Please feel free to post your questions in the chat if you're on Zoom, and later we'll have a Q&A. Lastly, the session is being recorded and will be available to you later on the Studio X website. And with that, I'd like to give the floor over to today's speaker, Dr. Parekh. The floor is yours.
Thank you so much. Thank you so much for the introduction. It's great to be here delivering this talk, and it's great to have this opportunity to talk about my work on audiovisual scene understanding and give a point of view from the AR/VR field and the work that's been carried out within the Meta Reality Labs. So let me complete from my side a part of the introduction, also taking us forward into what we'll be talking about today. So I'm a research scientist at Meta Reality Labs, primarily working on machine learning for audiovisual applications in AR/VR. And I did my PhD on, like was said, on audiovisual scene analysis. And these two will be the highlights of our talk today too. And in some spare time that I find, I also have found some interesting teaching opportunities. One is on math, music, and machines. So if you're interested in learning more about Indian classical music and how it connects with science, then please do come and talk to me or write to me. And I've had the privilege of presenting a tutorial at ISMIR with Professor Zhao and Bo Chen, who was at that time a PhD student in the audio lab, and also my advisor from Telecom Paris, Le Messid. So yeah, and with this, we'll get started. So with that out of the way, we'll be talking about audiovisual scene understanding today. And I've broken the talk down into broadly 3 pieces. So we'll start with the first one, which is the rather easy one, which is single microphone, stable third-person point of view videos. So in that particular case, we look at a few tasks and solutions and challenges, some of our work. And then we'll come to the more difficult case of multiple microphones and egocentric videos taken from the first-person point of view, which is where most of the Reality Labs work is. And so that will give us an introduction to what's happening in the lab. And finally, we'll take as a case study audio scene analysis and make some comments about how we look at it when looking at it from the point of view of AR/VR devices. And so my goal is to primarily give glimpses of research that is happening within the broad area of audiovisual scene understanding. Some of it will be my work, some of it will be the lab's work. So it will be a mix of two. And it'll broadly be arranged like I just described. And the secondary goal is to give an introduction to some open initiatives in the audio team that we have, where we can continue to collaborate as a research community beyond this talk. So I like to use this as an example to motivate audiovisual scene understanding.
Sanjeel, sorry to interrupt. But do you have slides to share? or it's just a presentation? Do you have slides to share?
So do you see the slides?
We can see the slides in the room.
I see. I guess I can't see the slides.
Oh, I see. Okay.
Can't see the slides. Or something.
Oh, now I see the slide. Sorry, I think I was in a wrong view.
Okay.
Yeah, about that.
Okay, great. Yes. So I hope it's all okay for everybody now. Yeah. Okay, great. So yeah, so I like to use this as an example to motivate audiovisual scene understanding. This is from a very busy street in India, and anybody who wants to navigate through this scene or get away from it would require multimodal perception to do so. And by multimodal here we mean audiovisual primarily, but you could have other modalities, motion sensors and everything else coming in also. So our goal is to impart this perception or this ability to machines. And that has its own advantages. And there's a whole list of advantages. Here it's just broadly structured under video structuring or video post-production, human-computer interaction, and so on. Right. So with this general motivation in mind, let's get started with the first case. Remember, we have a single microphone and these stable third-person point of view videos, which are being recorded using handheld cameras. So these are mostly videos that you'd find on YouTube, let's say. So you're given a video of an audiovisual event, and there are a set of questions that you would like to answer about these kind of videos, right? So maybe you'd like to know what kind of AV event has occurred in this video, or you'd probably like to know where the visual object is, or where is the sound event occurring in the temporal dimension, or what does it sound like, and so on. So you'd like to localize in the visual domain, you'd like to localize in the audio domain, you'd like to classify the event. In the data that you typically find for such tasks, again, single microphone, third-person point of view, the two things which normally happen. One is that the audio and the visual cues may not appear synchronously, which is to say that maybe the train horn sounds in the first second and the train is only visible in the last second of the video. So the two cues may not appear synchronously, and you may not have very fine-grained labels on such videos, right? So you may not know exactly where the sound event was to train a model to detect it, or where the train is in the visuals. So we need to overcome these kind of limitations when wanting to build such systems with, for example, YouTube data. And so there, what we are proposing is to propose and learn in a weakly supervised fashion, which is to say that if we consider a video as a bag of proposals, and by proposals we mean these are just segments of audio or segments of video where the object of interest might exist. And what we do next is we learn some features for these proposals, and then we want to score these proposals according to the class of that particular video. So if it's a train video, then I have an image sequence, I pass it, I extract all the proposals, I do some feature learning, and then I want to score each proposal, which is each video segment or each image segment, to say whether or not it's important for the final classification, right? And we do the same on the audio side, and then we can do a classification based training, right? All right. So this is just the intuition, and there is a particular, I mean, you can instantiate this whole system in a particular manner. Here, for example, we have a set of video frames. We do a bounding box for each of these video frames on the images, right? So each bounding box is a proposal. It could contain the object of interest. And there is, on the audio side, you could just simply chunk the audio, and each chunk could contain the object of interest. Then you can do some feature learning, after which you can do some scoring. So you can say for each class and each proposal, what is the score? So you have a class times proposal matrix, and then you can use a simple fusion strategy to do the classification and then train it using any particular loss that you like, right? So this is a deep learning system that that you can build while taking into account asynchronous event occurrence and non-availability of of fine-grained labels, right? So without going into much detail, this is just to highlight that such a system has shown strong performance on a few data sets, and that we can clearly see the audiovisual complementarity. So this is an example, and I just want to bring your attention to these rows highlighted in yellow. So you have vehicle sounds on top, which is one category of sounds, and warning sounds, which is the other broad category of sounds in this DK smart cars challenge data. And what we see is that there is, for vehicle sounds, there is a strong dependence on the visual modality. And for warning sounds, which could contain the same vehicle, so maybe a car beeping while reversing or a car alarm, so they contain the same visual object but different audio objects. So that's where the audio modality is more helpful. So this kind of intuitive audiovisual complementarity that we generally expect exists. Let me show some localization results, and this video will basically walk you through some of these results that I want to show here. So let me just stop here to give you an overview of what you'll be seeing. So on right-hand side, you will see the original video playing. On the left-hand side, you will see a subsampled version of it playing with bounding boxes denoting the proposals on the visual side. And on top, for each audio chunk, you'll see the score being displayed. The white bounding box on the visual side will show you the visual object that we are detecting, and a score of 1 will show you the highest scoring audio segment, right?
Safety equipment when you guys ride.
Right, so in this example that you'll hear now, you'll hear that the sound of the car is heard much before the car is fully visible. So this is the asynchronous cues that we were talking about. And here the visuals are going to be ambiguous, but you'll hear the audio. Right, so you don't see the object in the visual domain. Okay. So this was just to give an example of how we can identify, locate, and try to extract some audiovisual objects. Okay, now let's change gears, and let's say we have an audio scene analyzer given to us. So there is a scene in this very toy example. We have a dog barking in that scene. We have a baby crying and other events happening. All of these events are captured through a single microphone. We are still in that case. And we give that to an audio detector, which tells us that there is a car alarm in that scene, right? And now the question that we want to answer here is, what is the network listening to when it took this decision, right? So that's the question that we want to answer. This is a different problem, still in the single microphone case. And let's see how we can build a system to tackle this particular problem, which is that of interpreting the decisions of a deep network. So there are two requirements that we pose on the interpretations that we want to see. The first one is that we want to understand the network's decision in terms of human understandable concepts. So there should be some underlying human element to the conceptual understanding that we want to build for this particular system. And the second one is that we want to make it listenable. So this listenability is unique to audio, because if I showed you spectrograms, or if I showed you some numbers to say that, okay, this is what the network is listening, this is what the network is looking at to take this decision, it would not mean a lot, because we wouldn't really know what is, if the network took a rational, as in if the network took a proper decision or not. If it was listening to something completely arbitrary and it said that it's a car alarm or it's a emergency alarm, it would not make much sense to us, and we would not trust the system so much, right? So it's important that it's listenable and that we can judge for ourselves from the by listening to it, that whether it's something that is reasonable or not, right? So let's see. We are going to use NMF, which is a very popular audio source separation method, to accomplish this task. So a very brief primer on what NMF does. So given a spectrogram, which is here denoted by V, we can decompose it into two non-negative matrices. One which represents the spectral patterns. So this is a spectrogram which has frequency and the time axis, right? So there are spectral patterns in the spectrogram, and there are temporal activations of those spectral patterns. So both of those are the non-negative matrices that we can decompose that spectrogram into, right? So it's a multiplication of those two, matrix multiplication of those two elements. Okay. So now we'll use this idea and somehow interface it with the network that we want to interpret. And what is the intuition behind what we want to do? So here we are assuming that we are in this post hoc interpretability case where we are given a trained network that can analyze audio scenes. We want to learn a dictionary to model all audio objects in the scene. Okay, so maybe we have a data set and we learn a dictionary, which will be our NMF dictionary. So you remember that we can get these spectral templates or patterns. So we can learn these patterns over a set of data, right? So once we do that, we want to map the deep representations to NMF dictionary concepts, right? And once we achieve that mapping, then what we can do is we can use that mapping and the standard soft masking technique to listen to parts of the input that the network is listening to when it's making its decision, right? So now let's make things more concrete, and let's also listen to some example to make it very clear. Okay, so let's start with this. Input is X, which is a log-mil spectrogram. We have a classifier F, which has a certain number of layers. In this case, we're assuming it's a CNN-based classifier, which has a certain number of convolutional layers, and that's outputting a decision here, right? Now, what we want to do is we want to access some intermediate layers of this classifier and build a mapping from those layers to an intermediate embedding. Now, all this intermediate layer access and embedding is part of our interpreter module. So we want to analyze, given a fixed network, somehow be able to say that, okay, these layers contain representations of a particular object. That's the idea, right? So let's see, what are the conditions that we need to impose in order to learn such a mapping. So the first one, the obvious one, is that we need to ensure that this mapping that we built mimics the original classifier's output, so that we know that what we are trying to interpret is the correct thing. So we want that there is some output fidelity. So whatever the classifier outputs, we want our interpreter to also output the same thing, so that we know that, okay, we are understanding the network only and not something arbitrary that we are building otherwise on top, right? Because it could be some function that does some other kind of mapping, and it's not, there's no fidelity between the classifier's output and the interpreter's output. So that's the first one. And the second one is where we use NMF. So the diagram is now getting complicated. So let's highlight some parts of it that we want to look at. So the first thing that we want to look at is this W matrix of spectral patterns, which we have learned from input data. So we have a data set that we are training the model on the same data set, or that we train the model on the same data set, we can learn the spectral patterns. So these are the spectral patterns that we learned using NMF. And now what we do in order to constrain this intermediate encoding to have a mapping to the NMF dictionary concepts is that we ensure that these input representations of our deep network map to time activations, which is to say that these time activations are representing activations or not of a particular concept. And these concepts are these spectral patterns, right? So we can say that this matrix times this intermediate encoding that I want to learn should be able to reconstruct my input spectrogram, right? So through this constraint and this pre-learned dictionary, we can impose this constraint on our intermediate encoding that it should simply contain time activations of an NMF dictionary. So this is how we are creating this mapping from the intermediate representations to the NMF dictionary, right? So once we can construct such a mapping, we can also ask which are the most relevant components for our network's decision. So let's say the network took a decision. We know that we have the output fidelity here. So for that particular decision, we can go back and see which were the most relevant components, and then we can reconstruct using standard NMF techniques and see what the network was listening to. So if this did not make a lot of sense to you, or if it was too fast, let's take a very concrete example. I will leave the details for you to look into later, but let's first go to the example that we can consider, right? So this is the input where a dog is barking and a baby is crying. So this is the input to our network. This is the input spectrogram. First thing I'd like to motivate here is the idea of listenable interpretations. If I give you this input, and if I told you that this is my network's interpretation, or this is why the network said that it's a crying baby in this particular audio, you will not understand anything about this decision, right? But if I told you that you can listen to what the network heard as the input, this is what the network heard. Right? And this is what the network was paying attention to when it took this decision that there is a crying baby in this scene. Right? So this makes our understanding of what the network is paying attention to much clearer, and we understand very clearly that, okay, this is what the network was paying attention to. You can hear a lot more examples on a website that I'll share at the end. There are also examples where the network takes a wrong decision, and you can actually have an interpretation for why the network took a wrong decision, because the network was focusing on something that contained the characteristics of the sound that the network detected, which was wrong, right? So those are some interesting examples that you can look at. One interesting thing that comes out of this whole mechanism that I just described is that we can go back and evaluate how truly our interpreter is able to extract features that our pre-trained detector is relying on. So because you have the NMF idea where there's a decomposition, you can completely remove parts of the audio which are relevant, which your interpreter finds as relevant, and then try to see what the network's output is. So then you can see the drop in the probability values for that particular decision and so on. So this idea of faithfulness is something that we try to evaluate in this particular work. Okay. All right. So this was the first part of the talk, and our primary focus was single microphone, third-person point of view videos. we try to understand AV scenes using audiovisual scenes using deep networks, and we try to interpret deep networks that analyze audio scenes. So just to give you an example of what I mean when I say these third-person videos or single-channel audio. So this is the kind of videos that we typically see, right? I won't play the audio, but just for you to see that this is a very stable video shot from a camera about a scene that we want to understand. Okay. But in reality, like what we are experiencing is something very different. So what our eyes are seeing, or what our experience of the world is something like this, right? So it's always moving, the visuals. You may not always be looking at the object of interest. You have multiple channels of input. In this case, multiple channels of audio. That's what we'll be transitioning to, right? So there is a need to understand such scenes, and I'll come to the need and the motivation for doing all this, and how we are going about doing some of this in the Meta Reality Labs team, right? So now let's just shift gears. Now we are in the egocentric multi-channel case, and I'd like to start by stating what the Reality Labs audio team's vision is. So our vision is to enable effortless listening and realistic acoustic rendering through multimodal egocentric understanding, right? I'll go over each part of this vision that I just said. So each effortless listening, rendering, and then understanding. But first, we'll start with how can we go about recording such data, collecting such data, trying to understand the world from the experiencer's point of view, right? Which, I mean, just to give some motivation. So there is the experiencer's point of view. We want to, or we can enable immersion. There's all the kind of augmentation that we can do. And then it really personalizes the experience that you want to have of the world around you, right? So we'll talk about a few things in this part of the talk. The first one will be egocentric recording devices. How can we collect such data? And then for each of the parts of the vision that I spoke about, we'll touch over some of the tasks and data sets that we have, right? So let's start with the first one. So the project ARIA is what enables us to collect this data at a large scale in the wild. So these are these glasses that you see rotating here, which contain a lot of sensors and which are enabling us to overcome all the research obstacles that we have towards building this kind of augmented reality experience and the glasses product. And it also, as you can see, is power packed with a bunch of sensors. It's something wearable, so it's something that can go with you anywhere that you want. And so there are microphones, there are cameras, there are Wi-Fi, Bluetooth, GPS, there's eye tracking cameras. So there's a lot of compute and sensors and a lot of data that can be collected, which will be useful and can be useful in order to build some of this technology and some of the vision that I just spoke about in terms of listening and acoustic rendering, right? So given that we can collect all this data using these glasses, we want to do multimodal egocentric understanding, right? So I hope it's clear now that what we mean by egocentric. And now in this particular scenario, we want to understand what scenes are, what events are, objects, actions and interactions of humans and other objects around them, right? And so we have collected this very large data set. This is work over multiple teams at Meta and beyond, which is the Ego 4D data set, more than 3,000 hours of uncurated videos. And it comes with a benchmark suite. So there are multiple challenges which are running across this data. And these challenges will also give you a flavor of the different tasks which are happening around them. So this is something that everybody, all of us can collaborate together on. So one of the tasks that's running here is episodic memory. So maybe you left something somewhere, or you forgot your keys, or you forgot your the remote somewhere, and now you want to look for it, and then you can ask a question saying, where is X? And so then you can go back and retrieve information about where you probably left it. Then you can come to the present, and you can be talking about the actions that you're currently doing or the interactions that you're currently having. So there are problems like object detection, audiovisual diarization, or conversations and social interactions that you're having, which can also be solved using such egocentric data. And then into the future, you could be talking about what is it that you would probably be doing next. So you can see that audiovisual scene understanding, the problems that we just spoke about in the single channel third person point of view case, are still relevant. There are many more challenges because of the number of modalities and their nature changing in this particular case. And it's central to actually building this particular kind of understanding, right? So that's about egocentric understanding. The second part of it, or rather the first part of what we spoke about in the vision, was we want to enable effortless listening. And specifically for that, you can use these glasses to sit and have conversations or social interactions. And by effortless listening, what I mean is that in noisy environments, you want to be able to listen better, right? So you could do this for conversations. And in this case, there is a data set which is publicly released called EasyCom dataset. And there's a challenge running around it, which is the Spear challenge, which is microphone array recordings of people having group conversations in restaurant-like background noise, right? And this data set is coming with a lot of annotations. So it's coming with head bounding boxes or speech transcriptions, voice activity, annotations, and so on. So it's another thing that if you're into speech enhancement or any such problem, then you can really consider looking at this really realistic data collected using the glasses and multiple microphones. And for realistic acoustic rendering, first I'll let the video do the talking, and then we can discuss a bit more some of the tasks around it. Right. So what you saw was that you can actually use this platform to render audio sources in arbitrary geometries, material arbitrary locations, and it enables a bunch of applications. So some of these are already running as part of the Sound Spaces challenge. These are combined efforts across multiple teams, and the Reality Labs team is involved in all this. Some of these challenge tasks are around navigation or active audiovisual separation in unmapped 3D environments. So if you're interested, please do go ahead and look at this. So now we've talked about a bunch of tasks in a bunch of environments and scenarios. Let's just stop and take a moment to consider something that we know, audio scene analysis, and just consider what about it. It's a very, if at a very high level, if you just consider scene recognition, like it is in the DCase challenge, it is a simple task, simple in the sense of there is some data that is collected in the challenge. There are some models that you can build, and there's a certain performance that you can get. Beyond that, and in fact, there is a need to go beyond this for multiple reasons, and I think some of those reasons will become clearer as I walk through some of these thoughts that I have on using these known problems within the XR case or within any specifically novel use case, right? So the first thing is that audio is advantageous in such scenarios because it's computationally cheaper than video for scene sensing. So then you're looking at low power, low compute models for XR devices. And latency could also be a constraint depending upon what application we are looking at, right? Also, scene analysis, in this case, audio scene analysis or audio scene recognition, wouldn't just be a single component placed there wanting to know which scene the user is in. So that might have its own advantages and its own applications, but that is typically not the case. So these components are typically part of a much larger system. And so it's important to take system level interactions, system level evaluation, system level KPIs into account when looking at these things. And more generally, I think this whole space, what it does to known problems is primarily because of the user and the device being involved in this whole equation. So if you take any typical machine learning problem, there would be some data, there would be some model, and there will be some evaluation. In this particular case, because there is a user and the device, there's a certain behavior, certain interaction, and a certain environment that the device and the user exist in. That is what is telling us the kind of data that we need to train these models. It's telling us the models, the kind of compute size or the type that we need in order to cater to that particular application for the user. And also the evaluation, which needs to go beyond the lab settings. It needs to consider both system and component level evaluations. And so all of these together kind of form the final system that you'd end up building, right? So this was just to give a point of view for very simple looking audio problems, or at least simple looking in terms of their formulation. But there are nuances that need to be considered when we are looking at any specific application. And this was just an attempt at commenting on that a bit. Okay, so let me sum things up now. So we have talked about understanding audiovisual scenes through deep networks. We had talked about interpreting deep networks, which was primarily post hoc interpretability. But if you're interested, there is by design interpretability and a lot of experiments and evaluations in the papers that I'll cite. And then we spent some time talking about devices, data sets, and tasks that we are performing in order to enable egocentric analysis for AR and VR. And I think what I've done in this talk is, if audiovisual scene understanding was an ice cream shop, then I've primarily just presented different flavors or different kinds of ice creams that you could potentially be buying. And from my point of view, I think each of them is equally interesting, equally relevant. And it's up to you to pick the one that you like the most and continue your work on it. All right. Thank you. So before I complete, thanks to my collaborators and advisors. Thanks to Janeel, from whom I've taken some of these interpretability slides. And obviously all of the RLR audio team for allowing me to discuss some of their work as part of this presentation. Thank you. And yeah, for any references, you might want to look at this slide. But yeah, now we are open to questions.
Yeah, thank you, Dr. Parekh. So yeah, we'll open up for questions, but on Zoom, feel free to add something to the chat and turn the room. Are there any questions right off the bat? Matt?
I can start it off. Thank you so much for the talk. I was wondering if any of the kind of the potential applications are sort of limited by the network computational speed and that sort of thing. I guess what I was imagining is, say you have a driver and you're trying to alert them to say, hey, there's a car coming up from your blind spot, and so you'd like play a signal, so you'd have to sit there, detect the sound, recognize it, give it to the driver and then, have enough time for the driver to take action, that kind of thing. So how kind of fast are these networks, and do you see it in any way as like limiting for some applications such as that, or I guess
Right,
is
right.
an issue for any potential applications?
Yeah. You're right. I mean, so as far as the issue of what you can achieve with these devices, what kind of latency do you need? What kind of context do you need in order to take certain decisions? You're right that there are certain limitations to some systems, and it completely depends on how quickly can you process a particular audio event. So maybe you need more temporal context to process some. That's correct. So I think the idea of being able to show how uncertain you are when you're taking a particular decision also becomes quite important. So I think many of these issues go hand in hand, and to be able to give the user a complete picture in terms of what you know and what your limitations are is quite important, specifically for these kind of cases that you're talking about.
I can imagine it's tricky if you have like really short signals, I guess.
Yes.
Or,
Yeah.
that kind of thing where it's, it'll give its best guess, but maybe a person would have had a hard time guessing anyway,
Right.
Think, oh, there's something,
Yeah, and that just goes back to when you're building such a system, let's say for event detection for these sounds where you require very low latency, then it becomes all the more important to design your evaluation correctly, to design a lot of the other parts of the system, and to also know whether or not it's feasible using the current technology. Yeah.
Thanks.
Are there any other questions in the room? So actually, I have a question. So I guess I'll go ahead. So something you mentioned is that in your presentation is that usually weakly supervised networks are used. So I was hoping you'd comment a bit more on that. Why maybe a strongly supervised network uses this for generalization purposes, or I was hoping you'd talk about it a bit.
Yeah, sure. Yeah, so what I mentioned was that in cases where you may not have very fine-grained labels, so you may not know exactly where things were, you might want to use some approximate labels in order to zone down on the more exact localization of things. That said, in reality, to deploy these systems, you would actually want very strong labels, because you would want very good confidence on whether or not something exists or something is there or there, and so on. So you could employ different techniques, knowledge distillation, or so there are a bunch of self-training techniques or other techniques which you can use to get these more stronger labels in order to train such systems. So yes, you would want to be strongly labeled, but if you did not have the labels, then there would be ways of training such systems too. That was the idea for presenting that weakly labeled. Yeah.
Great, thank you. And then kind of like a small follow-up to that, like we've seen some of the videos, like how do these models perform when there's like maybe not great imaging conditions? Because it's like I come from an optics background, so that's always interesting to see. Like, if we have a video, if we have something that might not be the resolution quality that a human eye might be great at, like, is there, like, how are they limited, and is there maybe a hope that they can enhance what we can see as humans and kind of like push us beyond?
Right. So you mean on the visual side, whether we can enhance poor resolutions, or you mean that if there is a classification problem to do, then, and the visuals are not very good, then can we rely on other modalities in order to make those decisions?
I'd say on the visual side, kind of like the first part, that's like, can we kind of go beyond, like, I guess I'm thinking from like a user-centric perspective, right? Can we, because they're trained to something, but can we make it kind of like an enhancement of the human visual system rather than just,
Right. Yeah, sure. Right. So from my experience in the audiovisual field, I think that these systems are possible. Already, I think there is some work around this problem of super resolution. So wanting to increase resolution of images, videos, and so on. But also from the point of view of wanting to increase or go beyond the human visual system. I think in certain cases you can. In certain cases where it's, let's say it's dark and it's, I mean, really nothing is visible, then I don't really think anything can happen. But yes, I do think there are systems which can go beyond.
Great. And there was a question in the chat. Can you see the question in the chat for you?
Uh,
I'll read
all
out
right.
for everybody in the room. So what kind of machine learning models used for training audiovisual scene understanding that has audio-video latency mismatch? And what are some of the techniques, pre-processing, feature extraction used for these kind of latency issues in training the data?
The first part of the question is,
okay. Can you see that in the chat?
Yeah, I can see that. Right. So I think, okay, yeah. So there are various ways in which people try to tackle latency in audiovisual systems. So you could try to subsample the video or process it only when it's necessary, and try to do similar things on the audio side in order to ensure that you have similar latencies, or if one of the legs is lacking latency. Also, it's typically found that you may not always, so you can also make the visuals or the audio dependent on something in the scene. And so you may not always require as much compute or as much precision in terms of wanting to do a particular task. So all those things play into this latency equation. And I think it really depends on the target application, but depending upon that, you could decide. For instance, for speech enhancement systems, for most cases, not for very low SNR cases, but for most cases, maybe you can just do away with audio. So then you would typically just do that with audio. And when you encounter something very drastic, at that time, you would probably get your visual system into question. And then, yeah. I think the answer is really context dependent in this case. Yeah.
I have a question.
Yeah.
So in the egocentric audiovisual scene understanding, do you also work on, say, localization of sources and matching the sound source with the visual scene, like audiovisual association, this kind of task? And,
Yes. Yes.
Okay. Cool. Could you elaborate on this part? Because like in egocentric setting, the device is moving constantly, and I can see that the localization and association can be a challenge on both the audio and the visual modalities.
Yeah, you're very correct. And actually, that is one of the challenges of tackling this particular egocentric audiovisual localization and other tasks here. In fact, one of the papers that I'm aware of in this area is from University of Rochester. I think it is Chao Huang and Chenliang Xu. I think
they are in computer science.
Yeah, and together with Anurag, I think Anurag Kumar from the Reality Labs, they were working on this egocentric audiovisual localization. And I think one of the approaches is to use a strategy similar to what is used for single channel third-person point of view videos, but trying to stabilize the visual features or the visual modality a little bit using some techniques from visual processing. So I think robust visual processing, where even with everything else moving around, you can stabilize that stream or the frames which are really unstable, and also try to maintain some kind of asynchrony in the audio and the visual modalities. Because when the person is not looking at the object of interest, but it's still sounding, or vice versa, you can still make those associations back and forth in the, yeah. So I think those are some of the ways which are being explored currently in this area. Yeah.
Okay, yeah, thank you, Sanjeel. Can I ask another question?
Yeah, sure. Please.
Okay, so in our lab we work on HRTF personalization, header related transfer function personalization, and we were thinking that thinking about the possible applications of this personalization technique. I'm thinking maybe in mixed reality or augmented reality scenarios this could be useful. Like in Meta, do you have possible application scenarios that require this kind of personalized HRTFs, deployed into the headset?
Yes, definitely. Actually, so all this work that's happening around realistic acoustic rendering, quite a lot of it requires personalized HRTFs. So that is a good area of research for us too. And I do know, if I'm not wrong, there are quite a few publications from the team around this particular area. And so for all kinds of immersive applications, for all kinds of so all cases where maybe the person who you want to be talking to or what you want to be listening to is probably, let's say, in a different environment, or if it's in a different location where you want personalized sound. So all such applications which are under this particular area of what I spoke very broadly about as acoustic rendering, I think it contains quite a bit of application over there. Yes.
Okay,
Definitely.
thank you.
Yeah.
In the room? Yeah, I have another question. I have a few questions. So kind of one thing, because we're in a very interdisciplinary program, like I usually like to ask this, kind of like pushing for these tools and kind of like trying to push for AR and VR. What is the kind of vision you have for where the development of these models could take us? And maybe like, do you have some interesting applications that you're passionate about that you would like to see kind of go on in the AR VR world?
Right. Yeah, I think for me, what I really find interesting is some things that I've spoken about in this particular talk, which is exactly the vision of the lab, which is trying to enable conversations or other interactions or everything else in noisy environments, and also this ability to realistically render sounds, and which includes a bunch of these technologies that we just spoke about, from speech enhancement to localization, which Jia mentioned, HRTF personalization, which is again really needed in order to make somebody feel that a particular sound is coming from a particular direction and it's really personalized to their location in that particular room or in that particular space, and so on. So I think really the vision of the lab captures almost all of what I would actually say as an answer to this particular question. Yeah. And what's interesting to me is that, so let's say during my PhD or postdoc, I gave some thought to audiovisual scene understanding. But this particular paradigm of having these glasses on and being able to do in the wild recordings at every possible location, it brings a new set of challenges that need to be tackled for the same set of problems. And it is much more applicable because then you are actually the person who is experiencing the scene. You don't really require, it is something much more personal than anything that we currently have in terms of maybe the handheld devices. Yeah.
Great, thank you. Are there any additional questions that are on the Zoom or here in the room? So we have a question from Sarah.
Yeah, thank you for the talk. It was really interesting. I'm just curious, to help with localization, could you just add more microphones? Maybe
Yes,
on different places, yeah.
So you mean yeah? So let's say on these devices we have about, I think there are 7 on the one that I showed, and there would be about as many plus minus something. So also there are some limitations to the device in terms of the positions of the microphones, because there are multiple things on this very small real estate. And so yes, so after a point where you've reached those limitations, it's up to, I think, the models that we build in order to ensure precise localization. But yes, with the number of microphones, you can go up to a certain point in order to do increase. Yeah.
Okay.
Do we have? Oh, there is a question in the chat. So I'll just read it out for the room because people cannot see it, and you can take a look. So the question from James is, I want to know more about how these methods visually scale. Most of these examples try to do scene understanding from a room scale or broader, excluding the Ego 4D methods.
So I think I understand the first part of the question. When you say most of these examples try to do scene understanding from a room scale, room scale versus smaller in-person view. Oh, so you mean in terms of field of view, maybe that you have the field of view of a person and the field of view of a whole room?
I can try to, sorry, I typed it kind of quickly, but if I'm trying to build a model to do scene understanding in a, like just evaluating something that's right in front of them, like a first person viewpoint versus trying to do maybe a full scale room or doing a house walkthrough, is there any kind of difference in the training methodologies or the data set that I might have that is visibly, tangibly different between doing these smaller scale in first person kind of viewpoint things or these larger room scale kind of view things?
Right. So while, I mean, I've not specifically worked in this situation or worked with a lot in the situation that you're talking about, but when I think about it, I think there is a lot more information to exploit in the room scale thing. But at the same time, you may have limited information in the first person point of view, but the person's movements give you a lot of information about the behavior or the interaction of that person with the scene that he or she is experiencing. So there is a trade-off in terms of the amount of information, visual information that you have. So for example, I can take an example here. There was a paper from the team, I think 2 ICASP 2022 maybe, which was around using egocentric visuals to know what is producing noise in a scene and suppress it. So let's say you are having a conversation and there is some things in the room which are producing noise, and so then you can use egocentric. So the paper was exploring whether it's possible to use egocentric visuals to spot the noise sources, because you can visually see the noise sources, and then try to suppress it. When you talk about room scale, maybe you'll have much more information about the noise sources in the room or other sources in the room, and not just from the person's point of view. So maybe you are able to do a much better job on this particular task. But at this point, I'd say that I think it's coming with the limitations of the device itself, because if the device can only give you so much, then the question would be that, is it possible to work with what you have? Or yeah, like you said. So at that point, I'd also like to say that it is possible to take advantage of both room scale and small person point of view while you're training the system, right? So at that point, you can take advantage of all the data that you have. And so there, you would use all this information that you have available, whether it's from the point of view or at the room scale, in order to construct a more robust system. So that's also another possibility. And you're right that I don't know if that's already if that's answering part of your question or not, or if it's
oh no, that's definitely answering my question. Absolutely.
All right. Okay.
Just quick follow-up question.
Mhm.
So you brought up how there's differences in the things that you'd be able to take different parts of the day that you'd be able to take advantage of in a room scale versus a smaller first person view. Could you envision a transfer learning kind of methodology where you could say, I'm doing these kind of things in a room scale system, and I'm trying to adapt that for a smaller scale system. Let's try to take the same model and adapt it for this new format.
Yeah, surely. I mean, I can imagine that you could build such a system, and if not, it would at least be a baseline that you would compare against if there is something better that somebody can think of. But yes, definitely, I think that would be an approach.
Got it. Thank you for the talk.
Thank you.
Do we have any other questions on either Zoom or in the room here?
Messages in the chat. All right.
No, we've gone through the chat. Yeah.
I suppose I have one more question. So at least typically from what I've seen in machine learning, a lot of trouble comes into basically just like having good training data sets is really one of the big things. So I was wondering if you could comment on that and, you know, how hard, you know, how hard it is to find, you know, high quality training data sets, and basically everything that I guess goes into that.
Yeah. That's a very pertinent question, and it's something that you encounter almost every day when you're building these systems, that the data that exists online. So for a very simple case of audio scene analysis, if you took YouTube videos and trained a system on that, and then you try to deploy that system in the real world, it would really not do well at all. And so it really requires hours and hours of data collection, data annotation internally to actually be able to build a system that's deployable in the real world. And there are a lot of nuances there to how you construct the training data set, how you're trying to evaluate things, how realistic is the data, what are the kind of trade-offs you've made, or what are the kind of assumptions that you've made while capturing the data, which also go into the final model that you build. So yes, there are all those challenges to be tackled with every single problem that you want to tackle beyond research, for sure. And that's one of the reasons why the team has open sourced so much of its data, because we do realize that there is not going to be a very high quality of egocentric data, or high quality, large scale, and so on, if we don't use the infrastructure or the technology that we have at our disposal in order to collect and also let the community kind of contribute and collaborate on these questions. So definitely, that is a big question to be answered for every problem. Yeah.
Thanks.
We have more questions. Okay. Well, seeing that there are no more questions, let's thank Dr. Parekh. Thank you for a great talk. This was, I think, very interesting for all of us. And thank you for coming out and speaking with us. So if you'd like to continue following Dr. Parekh's work, there is information on the StudioX website. I believe there will be a link in the chat coming up soon, and his contact info should be in there. As a reminder, this was the last talk from the Voices of XR series for this semester, but please check out the StudioX website. You'll see all the past talks along with the recordings that are available. And all the links should be available in the chat, and for you in the room, they should be available on the StudioX website. Thank you so much, Dr. Parekh. We hope to have you again soon. And yeah, thank you everybody for coming.
Thank you so much for having me. It was a pleasure. Thanks, y'all, for the invitation. Thank you.
Yeah.
And if y'all didn't already, please make sure you sign.
Thank you, Sanjeel. Nice meeting you.
Nice meeting you too. Thank you. Bye.